This
Okay, I just started a video recording of the call so that I can post it later. As usual, if you want to throw in some questions into the chat box, please feel free to do it, and I'll consider that like a question queue going forward. One of the questions that didn't get answered in class today that, well, when I say in class, I mean the review session, was multiple choice question number 5 from review packet number 3. So I've got it queued here in front. You can see that it says that there's a 10-kilogram box and that it's sliding to the right along the floor, and a horizontal force of 10 newtons is being applied to the right. The coefficient of kinetic friction between the box and the floor is 0.2. The box is moving, how is it moving is essentially the question that's being asked. One way to think about this is that let's use the sketch as a free body diagram. We've got a frictional force acting to the left. We just don't know how big it is yet. Clearly, if the frictional force is equal to 10 newtons, then the net force on the block in the horizontal direction, the direction of motion, will be equal to 0. And then we can say constant speed and constant velocity. By the way, this question right here, or sorry, this answer B, which is about centripetal acceleration, is something that we're just about to start spending a lot of time with. These are accelerations that cause turning only. B is not going to be the right answer because this is moving in a straight line. It's moving to the left or to the right. Well, actually, it's definitely moving to the right. The question is, how is it accelerated? Is it slowing down or speeding up, et cetera, et cetera? So if we could figure out the frictional force, we'd be in good shape. And we can actually quickly figure out the frictional force. Let's remember that friction is equal to the product of mu and the normal force. And in this case, if I were to draw in some additional forces, the normal force would be up and the weight force would be down. The weight and the normal force are going to have the same magnitudes because I'm on a horizontal surface. And the weight is mg, and if we use g as 10, that's going to be 100 newtons. So we can see that the weight is 100 newtons, and therefore the normal force is going to be 100 newtons. So when I plug that in, I can see that the frictional force is going to be 20% of 100 newtons, which means that the frictional force is equal to 20 newtons. So let's go back to our sketch. If we go back to our kind of free body diagram slash sketch, we can see that we have not drawn that in properly. Conceptually, this is a larger frictional force acting to the left. It's 20 newtons. Therefore, the object's moving to the right, but the net force is to the left, and we're going to have a negative acceleration or an acceleration to the left. So if you have any follow-up questions to multiple choice question number 5, please cue it in the chat box. Also, there are no questions yet in the chat box, so I'll kind of wait. I'll wait for you guys to add them. All right, packet 1, this is Colin's question, packet 1, number 11. So I'm going to switch to that one. So I just switched my view so that I'm looking at the packets. I'm looking at packet number 1. I want to make sure that that's what you guys are seeing as well, because I shared my, I'm just using the app. So I guess what the question that I'm asking is question number 11, which is almost here. Can you guys see this question? So a yes or no will do. I just want to make sure you're seeing the right thing. Okay, not seeing it. Let me switch this. All right, let's try that. Are you seeing question number 11? Okay, good. All right, thank you. This is a Atwoods machine problem, not too dissimilar to the one we finished our review session this afternoon with. we can see that we have a block of mass 3m that's on it's on the table, and the table doesn't have any friction. The block is attached to another mass of mass m by a cord that passes over a frictionless pulley as shown. And they say if the mass of the cord and the pulley are negligible, what is the magnitude of the acceleration of the descending block? In other words, they're asking us what the acceleration of that block is. Now, for starters, your instincts at this point should be the acceleration of the falling block is going to be identical to the acceleration of block 3m at the top. Those accelerations have to be the same. And the reason is they're attached by a string that's not stretching. Again, as we've been discussing in class and you know, in our review session after school today, whether you were there or not, one way of thinking about this is that we have a mass of 3m attached to a mass of m, and that is effectively our system. I'm kind of drawing a box around that and saying, hey, we're going to call that our singular object. Yes, we get it. They're two separate objects attached by a string, but for this problem, we're just going to consider them as one. And the only accelerating force is this force right here, little mg, or just 1 mg. That's the only accelerating force. Are there other forces acting from outside the system? Yes, there's a weight here that would be 3 mg, and there's an equal magnitude normal force that cancels out with 3 mg, but those are not accelerating forces. Those are forces that are perpendicular to the direction of motion. So I've kind of conceptually generated this model right here, which is kind of the way you should be thinking. And I introduced this in the review session. Here's another way of thinking about it. You know, we can just say that the mass of the entire system is 4m, and it's being accelerated to the right by a singular force of mg, the weight of the smaller block. So, you know, when we kind of follow our system for answering these questions, we can say, is the sum of the forces in the x direction, or the direction of motion, is the sum of the forces equal to 0? And the answer to that question is no, it's not 0, because there's only one force acting in this kind of x direction, and that's mg. There's no friction, it can't be in balance. So I'll write my dynamics equation by saying that mg is equal to F net. And furthermore, I can say that mg is equal to the mass of the system, which would be 4m times my acceleration. We can see that the mass cancels out and the acceleration is 1/4 of g, or g over 4, which is where choice B becomes our best answer. Colin, make sure that I've answered your question and you don't have any follow-up questions. The next question that's in the queue is from Neha. It's packet number 2, question number 3. And Nika asked about question number 4, so we'll do both of those. We'll do 3 and 4. And while I'm on, so let's do those, and then I'll come back to answer Lauren's questions about 12 and 13. So let's see if I can figure out this flipping packet. Let's see, what was it? Packet 2, 3, and 4. All right. So I may have to shut off the screen sharing and then switch it back on when I have the right screen to share. All right. So you should be able to see that. Let's get to questions 3 and 4. Okay, so here it is. Question number 3 on packet number 2 shows a ball that's initially moving to the right, and they tell us that it's moving with the initial velocity vi as shown. It's then struck by a stick, and after leaving the stick, the ball moves vertically with velocity vf, which is smaller in magnitude than vi. So which of the following vectors best represents the direction of the average force that the stick exerts on the ball? We're being asked a force question, but because of Newton's second law, we can think of this really as an acceleration question. Whatever the change in velocity is, let's remember that by definition, acceleration is a change in velocity over a time interval. So whatever direction the change in velocity was, whatever the vector direction of the change in velocity, that's got to be the vector direction of the acceleration, which is the vector direction of the force, and that's basically what we're trying to answer. What's the direction of the force that's acting on the ball by the stick? So this is in some ways kind of a vector addition problem. Our initial velocity vector, I'm going to call this one here, it's VI, and we have to add something to it. We're going to have to add something that I'm going to call the change in velocity. I think you guys have kind of seen this before. So the question is, what do I have to add to that so that the final velocity is up? Well, one way of thinking about it is my initial velocity is horizontal. I got to get rid of all of that horizontal. So whatever the change in velocity is, it's going to have to be a leftward velocity. The x component of that velocity is going to have to be leftward so that it cancels out the initial rightward velocity and leaves me with no horizontal velocity. Additionally, it's not going to have just an x component. It's going to have a y component, and the y component is going to have to be equal in magnitude to VF, to this one right here, because it had initially no velocity, no vertical or y component of velocity, and then after the event, it did. So look what happens here. The V initial x, which is all of V initial, cancels out with the x component of our change in velocity. So then all that's left is the y component of our change in velocity to produce our final velocity. So that means then that whatever we add to it, our change in velocity is going to be have to be up and to the left, which is our acceleration and ultimately our force, and that's where B comes into play. So make sure, Neha, that I've answered your question for number 3, and I'm going to move on to question number 4. Which shows an Atwoods machine. Keep in mind, by the way, we've had 2 Atwoods machines questions on a review. The chance that you could get through the test tomorrow, not even mentioning like future tests like the midterm exam and then the AP test in May, the chance that you get through that without an Atwoods machine is pretty close to 0. So, my thinking is beef up on Atwoods machines to the point that you look at them and you're like, sweet, I knew it was coming and there it is and I'm ready for it. So that's good that we're getting the questions, but make sure that you leave the session or you at least show up for the test with a strong command of Atwoods machine questions. Cassie has a follow-up question, which I think is a very good one and worth this kind of short interlude. She's saying, hey, how do you know it's B and not D? And one of the kind of big ideas is, if I redraw that kind of sketch, I'll make it very quick because we saw it already. So here's V initial. We're going to have to add delta V to it so that we get, this small upwards. Well, when I say it's small, it's smaller. B is a lower angle. Let's call this our angle theta. So theta is a smaller value for B than it is to D. Notice that the y component choice in D, the y component is larger than the x component. And we were told in the problem that the final velocity has a smaller magnitude than the initial velocity. So that little piece right here, this little statement right here effectively eliminates choice D, because the smaller y component is only true in case B. So therefore, whatever we added, and I kind of drew these in these red colors previously, whatever we added here, that x component that cancels out with VI, that's got to be bigger than the y component that we add. And so therefore, D is not a valid choice for that reason. Cassie, make sure that I've answered your question. We're going to go on to Nika's question number 4, which says 2 0.6 kilogram objects are connected by a thread that passes over a light frictionless pulley as shown. The objects are initially held at rest, and a third object with mass 0.3, so we add this little piece on right here. And when we add that little piece on, then of course the system starts to accelerate. We're going to define our positive direction this way. They want to know the magnitude of the acceleration of the 0.3 kilogram object. So let's again remember that the acceleration of all objects in the system is going to be identical. And so therefore, you know, one way of conceptually think about it, I think I like this new method. We're going to call the object a single 1.5 kilogram object. It's clear that everything's going to accelerate, so I'm just going to add the 0.6, the 0.6, and the 0.3, which gives me 1.5. Now I'm going to draw these forces in. There's a weight vector, mg, that's due to both of those guys together. I mean, I could technically draw them separately if I wanted to. I could say there's 1 6 Newton downwards force from the blue block, and additionally there's a 3 Newton downward force from the red block, and so obviously the combined force is 9 Newtons downwards. Not only is there that, but there's the 6 Newton force on the other side, and that's technically the negative direction. So, you know, one way of thinking about it is, you know, I've got 6 Newtons going this way, and I've got 9 Newtons going that way. The leftover force, or the net force, is equal to 3 Newtons. And so I'm going to set that equal to mass times acceleration, where the mass is 1.5, and I can solve for the acceleration of the system. It's 3 over 1.5 kilograms. I left the units out, and I get an acceleration of 2, which is why choice D is the best answer. If I wanted to kind of be a little bit more formal in the way that I wrote that, you know, what I've done in the cloud here is, you know, my attempt at conceptually explaining an Atwoods machine problem so that you could quickly arrive at an answer on a multiple choice question. But if this were an FRQ, and you had to show all your steps, I just want to make sure that, you know, I can show that my dynamics equation will be a little bit more formal. I would say, you know, let's just for sport call the red block object 1, the blue object object 2, and the purple one on the other side object 3. My formal definition would be, you know, m1g plus m2g. Both of those are accelerating the system in the positive direction, minus m3g is equal to the net force in the system, which is equal to the total mass times the acceleration. And of course, you know, the total mass can be written as, you know, m1 plus m2 plus m3 times the acceleration. So, you know, when I plug these numbers in, m1 is 0.6 and g is 10, that becomes 6 Newtons, that becomes 3 Newtons, this becomes 6 Newtons. And I mean, we get to the same place. I'm just showing perhaps a little bit more formal way of getting there. So m1 plus m2 plus m3, of course, is 1.5. This is really the same problem, just slowing down and solving it a little bit more traditionally algebraically, where what I've done inside the cloud here is more of a conceptual approach. Nika, make sure that I've answered your question and that you don't have any follow-up questions or anybody else has follow-up questions on numbers 3 or 4. And I will move on. Okay. The next question brings us back to packet number 1 on questions 12 and 13. Okay. So I'm looking at question number 12, and both 12 and 13 reference a 3, 4, 5 right triangle inclined plane. They tell us that it's 5 meters in length and a block has a weight, not a mass, of 20 newtons, and it's allowed to slide down. The mass of the block. So question number 12 is a fundamental question about whether you're able to decipher or distinguish between mass and weight. So let's have a short conceptual discussion. Algebraically, the answer to this question is pretty straightforward. Hold on a second, I gotta get rid of this. Okay. Algebraically, its weight is equal to m times g. So in this problem, they gave us the weight, it's 20 newtons, and we're trying to answer what the mass is. And if we use g as 10 meters per second, we get a mass of 2 kilograms, which is where choice D is the best answer for question number 12. A better way of kind of approaching this, even though the algebraic one yields a very quick and quick multiple choice answer. Fundamentally, weight is a force. It's a downwards force towards the center of the Earth due to the gravitational force of the Earth. All of this, of course, isn't new to you, but be careful with the language. Objects have mass wherever they are. That's fundamental. So I can take a baseball to the, to orbit in Earth. You guys have seen videos of astronauts in orbit and the experience of weightlessness, which we'll be discussing in more detail in this next unit. So things don't fall. I've seen videos of astronauts brushing their teeth and they just kind of sit there and leave the toothbrush out and it's floating literally in front of them, and then they grab it and brush their teeth. So, there's no downwards force there. They're experiencing weightlessness. A better example, to be honest, would be in interstellar space where the gravitational forces are very, very weak and negligible to the point where we can ignore them. Mass, on the other hand, has to do with inertia. Oftentimes you'll hear the kind of coupling of the word inertia and mass. You'll hear it called inertial mass. It's the property of an object's mass. I'm defining inertia. It's the property of an object's mass to resist a change in its state of motion. So it really describes how much it just doesn't want to accelerate. That's another way of thinking about mass. Okay, that's question number 12. Let's go to 13. They want to know the normal force exerted on the block by the plane. Let's remember that the normal force is always perpendicular to the plane. The weight force, or mg, is directed downwards. We weren't really told anything about friction, but whether there's friction or not on this, it's not going to affect the y direction. So the normal force is there. A classic mistake to make is to answer choice D, 20 newtons, because of course you've been trained and have seen a lot of problems on horizontal surfaces where if the weight is 20 newtons, the normal force is always 20 newtons because it's not vertically accelerated. So that's kind of bait that you shouldn't take. It's got to be less than 20 as I'm on an incline. We demonstrated this actually using a digital balance in class today. It certainly shouldn't be more, although maybe that's not intuitive, but I think you can pretty easily eliminate choices D and E. We have to recognize that on an inclined plane, the perpendicular component of the weight, let's remember that on inclined planes, we rotate our coordinate axis and the weight vector is now in the third quadrant. And so I can resolve that third quadrant weight vector into X and Y components. I'm going to call this one mgy, and I'll call that one mgx. So the normal force in this case, which is perpendicular to the plane, is going to be equal in magnitude but opposite in direction to the y component of the weight vector. So really this question is, could be boiled down to, can you figure out what the y component of the weight vector is? Because that's equal to the normal force, and that's going to be equal to mg. Normally for the y component, we'd use sine theta, but because we're on an inclined plane and the weight vector references the y-axis, we flip-flop our trig. and we get mg cosine theta. M times g in the problem is given to us. It's 20. So, I can either, take 2 again from this problem and multiply it by 10, or just replace m and g with 20 newtons, and then I'm going to multiply it by the cosine of 37 degrees. And when you do that, you get a y component and an answer of 16 newtons. So make sure that I've answered your question on that one, Lauren, on 12 and 13. Okay. Allie has asked a question about packet number 3, question number 4. So I'm going to kind of flip to that one. Okay, I'm on packet number 3, question number 4. This is an elevator question. A quick sketch, a quick free body diagram would be helpful here. So here's our elevator, and we're going to say that there's a cable pulling up, and there's of course a weight vector going down. So the fundamental idea is that there's an interplay conflict, if you will, one pulling up, one pulling down, between the tension vector and the weight vector. We're told the elevator accelerates downwards at 2 meters per second. So we know then that the weight vector has to be larger than the tension vector. Of course, there's a leftover force. We don't draw leftover forces on free body diagrams. The reason is that a common misconception among first-year physics students is that a net force is a separate force, an actual force, when in fact we know that a net force is simply the kind of mathematical leftover or output from multiple forces acting on something. So I'm going to draw this off to the left in poor form here. I've got a leftover force, something downwards, because of the difference between the weight and the tension force. There's some good multiple choice kind of test taking strategies here. For starters, we know that via Newton's second law, the net force and the acceleration vectors have to be identical, right? So we've never pushed on something to the left and it accelerated to the right. So those two vectors have to share a direction. And we're told that the acceleration is downwards. So therefore, the net force has to be downwards. There's another cue. The force exerted by the cable on the elevator. So the question is, what's the force of Ft? Well, I think, maybe this is a little bit, tricky for first year physics students, and that's okay. But the tension in the cable is always pulling up. A rope, think about trying to push on a rope, right? There's almost like an old adage or a saying about being foolish by pushing on a rope. In this case, the rope can only pull the elevator up. It can't push it down. So I think it's good to eliminate choices D and E simply based on the vector direction of the tension. If I were to write a dynamics equation on this one, they want to know the force exerted by the cable or the tension force. If I were to write a dynamics equation, it looks something like this. I'm going to choose downwards as positive and upwards as negative. I'll explain why I do that, because I like the direction of acceleration to be positive. I find that more students make fewer mistakes when the direction of acceleration is positive, but we'll do it the other way too. The kind of other way being the kind of traditional method of up, thinking of a kind of y coordinate axis. Y is up, positive y is up and negative y is down. But let's go the other way first and assume that positive y is down. That means my dynamics equation becomes weight minus the tension force is equal to our leftover force, where weight, of course, is mg. We were given the mass of the elevator, it's 800 kilograms. Tension is what we're looking for. and F net is mass times acceleration. So we really have everything we need. We have M, A, M, and G. We can solve this for the tension force by adding it to both sides, and I get M of 800 times 10, that's going to be 8,000 newtons. I'm going to subtract from it MA, it's 800 times 2, which is going to be 1,600 newtons. And that's going to be equal to FT. Give me a second here. FT. So I get a leftover force of 6,400 newtons. And that's, sorry, not my leftover force, but that's my tension force. I'm sorry. So, you know, then the only other part here is that they express these answers in, you know, metric prefixes. It's a bit uncommon to discuss this in kilonewtons, but we can see that's where answer C comes into play. So make sure that I've answered your question. This is Allie's question on number 4 from packet number 3. I've gotten another kind of question about when I say the mathematical output of all the forces, would that mean F net is different depending on its direction, or it's just the sum of all forces on the object regardless of the direction? So this is a question that I just got. I'll rephrase, I'll say it again in case you didn't get a chance to tune in precisely about what was being asked. The question says, when you say that the mathematical output of all the forces, would that mean F net is different depending on its direction, or is it just the sum of all the forces on the object regardless of the direction? Force is 100% a vector quantity, so a net force of 3 newtons to the left, even though it has the same magnitude of a net force of 3 newtons to the right, creates totally different outcomes, right? One accelerates to the left, one accelerates to the right. So so I guess the short answer to this question that I've kind of received offline is, when you add up all the forces, or when you say that some of the forces is called our net force, the direction is an integral part of that answer, and should not be separated from it. So hopefully that answers your question about net forces there. Okay, so I'm at the end of my list. I'm going to give you guys, I'm going to take a sip of my tea, and I'm going to see if there are additional questions that pop up on the chat box, and then we'll go from there. Okay, not to do FRQs, Cassie's question, is there any chance we'd have an Atwoods machine on an inclined plane problem on the test? Let's take a look at FRQ number 3 on packet number 1, because I don't remember it. Switch to it. So one of the questions that I got, specifically Cassie's question on this Atwoods machine problem, is there any chance that you get an Atwoods machine problem on an inclined plane like this on the test? So I always want to be careful, of course, because I very much appreciate your job, which is, you know, trying to do everything you can to be in the best possible position to do well on the test, without giving away answers whether something like this is on the test or not on the test, um, let me at least say that this would be fair game. I would consider this a very challenging problem for AP Physics 1 students. I wouldn't consider it like evil or the I wouldn't even call it ridiculous. I would just say it's a tough problem. It's probably on the upper end of most students' abilities. So I think that it's fair. And so in this type of a question, you're being asked immediately what the tension is in the string. Um, the difference is, though, in this problem, um, they say that the boxes remain at rest. So I think at first this makes it a lot easier. They give you these coefficients of friction, and they say that the system is at rest, and they want to know the tension of the string. Well, we know that if something's not moving, that the tension vector drawn here and the weight vector here have to be the same. And so, it starts off kind of easy. And I think that this happens a lot on tough questions on FRQs. You'll look at the sketch and you'll be like, oh my God, look at this ridiculous problem I have to solve. I'm terrified. And then the first question, part A, is absolutely a softball, right? Like you read that and you're like, oh, okay, not too bad. So I find the harder the question, the easier the lead off part. That's kind of standard fare. Um, let's take a look at parts B and C and make quick work of it. Um, so look at part B. I think B illustrates this really nicely. It says, um, on the diagram, draw and label all the forces acting on the box that is on the plane. Um, and so since it's not moving, if there was no frictional force, you could actually calculate and show that the tendency of the system would be to move up the incline. And so, you would need to recognize that if that is the case, then the static frictional force labeled here has to be down the incline. The normal force, of course, perpendicular, tension force parallel and up the incline, and weight vector down. So B is just a straight up draw a free body diagram. Notice that I didn't resolve that weight vector into its X and Y components. The College Board tends to look on that poorly. So draw, when asked explicitly to draw a free body diagram, don't resolve forces into components, just leave them there. Then part C says determine the magnitude of the frictional force acting on the plane, on the box on the plane. So, well, when nothing's moving, we know that the tension force of 100 newtons is the same as it was in part A. So that's not, too bad. And then we know that the parallel component of the weight, mgx, is mg sine theta. And the reason is, again, we talked about this earlier, we flip-flop our trig because on an inclined plane, the geometry when referencing the y-axis with the angle theta creates trig components that are flipped. So that's mgx, and then this is all, and then there's friction on here, and that's what we're looking for, and they all add up to 0 because it's not moving. So we just flip that onto the other side here. We add that over, and I think it's pretty straightforward. So my initial assessment of the problem when I looked at it was like, okay, that's pretty tough. But I think as it turns out, when you take a closer look at it, it's a pretty doable problem. So make sure that I've answered any questions, or if you have follow-up questions on that. I've, in the meantime, had a few other questions that have popped up. Let's take a look at a few of these other ones. Here's packet packet 1, question number 17. This one is kind of a classic question. And they say that a rope of negligible mass supports a block that weighs 30 newtons as shown above. The breaking strength of the rope is 50 newtons, and they want to know what the largest acceleration of the block can be without breaking the rope. So let's start by drawing a free body diagram over here. So I know that there's going to be a tension force directed upwards and a weight force directed downwards. The weight force has to be smaller than the tension force, right? Because it's accelerated upwards. I'm going to use my traditional coordinate system. This becomes Ft minus W is equal to a leftover force of F net. And in this problem, they told us that the maximum acceleration occurs, the maximum tension that can occur is 50 newtons. So that's what I'm going to put in here. That's when I'm accelerating the box upwards the most. So I know what that is. I know what the weight is. And of course, F net is equal to mass times acceleration. So really what I'm doing is I'm solving this thing for acceleration, and I'll just divide both sides, both of those known forces there, divide them both by the mass, and I'll be able to figure out what the acceleration is. So the tension is 50 newtons, the weight is 30 newtons, so the numerator of that fraction is 20, and the mass is going to be equal to 3 kilograms, right? So mg is the weight, so if the weight's 30, then this is 3 kilograms, and so I get 20 divided by 3 is equal to the acceleration, which is just under 7, and that's where choice B is our best answer. So that's question number 17. Let's take a look at question number 19, and then we'll go to a different packet. Question number 19. Question number 19 is one that should have been eliminated from this. Question number 19 actually is a rotational mechanics question, and you would not be able to solve this until later on in the course. So 18 is fair, but then 19 requires this additional kind of knowledge base. So the question is, there's this board, and the board has a weight, and the weight of the board here is directed at its center of mass, 125 newtons. We know that the board is 4 meters long, and there's also a person with a weight of 500 newtons that's sitting somewhere on the board. We don't know where, but so there's a total of 625 newtons of downwards force between the board and the weight. The tension in the right chain is 250. So the left chain, we have to add the 250 to get up to the 625 newtons. But then question number 19 asks about how far from the left end of the board. This is a rotational mechanics question where we're going to be talking about torques. No, that's not a good question, and it shouldn't be on the review packet. So I'm just gonna skip that because I don't think it would be fruitful to spend some time learning about rotational mechanics when it's really not testable. The next question I'm going to look at is packet number 3, question number 9. All right. All right, here's packet number 3, and let's bring up question number 9. There it is. We've got our systems question. which always shows up. Let me make sure that I've shared this. So question number 9 shows two blocks of mass 1 and 3 connected by a light string. The light string has a tension of 2 newtons. So they kind of gave away the connecting tension. Oftentimes we're asked about what that tension is. But I could draw just a free body diagram of the 1 kilogram block. Of course, there's a weight vector going down and a normal force going up. And those two things cancel each other out. The only accelerating force is the 2 newtons of string tension. And so I could say, is the sum of the forces in the x direction equal to 0? The answer to that is no, because there's only one force. It's 2 newtons. It's acting to the right. So it's going to be, my dynamics equation would be tension is equal to the net force, or tension is equal to mass times acceleration. And I can calculate what the acceleration is. If this is 2 newtons and that's 1 kilogram, we can see that the acceleration is equal to 2 meters per second per second. So now I'm going to redefine the system. Instead of just looking at the 1 kilogram block, we're going to look at all 4 kilograms. Yes, there's a string connecting the 3 and the 1 kilogram block, but we don't care. We're just going to treat this now as a single 4 kilogram block. Force F is pulling it to the right. Yes, there's a weight vector down. It's 40 newtons. There's a normal force up, also 40 newtons. So the question is, what does that force need to be in order to accelerate it to the right? So this is going to be equal to F, whatever that force is the net force, or the mass in the system times the acceleration. F is going to be equal to 4 times my acceleration of 2 meters per second per second. And so I get a force of 8 newtons for question number 9. So make sure that I've answered your question about FRQ, not FRQ, multiple choice question number 9. And I think my last question of the night is going to be Lindsay's question on packet number 2, question number 2, and we'll go there. Okay. Here is packet number 2, question number 2. We can see that we again have a system, and 20 newtons is pushing the system to the right. There's a 3 kilogram block and a 2 kilogram block, and then we're asked this kind of awkward question. The force that the 2 kilogram block exerts back on the 3 kilogram block. So that reads a little peculiar, it reads a little weird. So when you kind of see that, you should be thinking, oh, okay, well, this is written in kind of Newton's third law context, right? The force of the 2 kilogram block on the 3 kilogram block is the same magnitude but opposite in the direction of the force of the 3 kilogram block on the 2 kilogram block. If I were to draw a free body diagram of the 2 kilogram block, the force that pushes it to the right is the force of the 3 kilogram block on the 2 kilogram block. That's the one, that's one that I'm looking for, because once I know that number, it's equal to the same as the force of the 2 kilogram block on the 3 kilogram block. So let's analyze it. I've got a weight vector down and a normal force up. They cancel each other out. And I can say that the force that I'm interested in, F of 3 on 2, is the net force, and that's equal to the mass of the 2 kilogram block times the acceleration of the 2 kilogram block. So I'm looking for this. I know that the mass of the 2 kilogram block is 2 kilograms. If I knew the acceleration, we'd be in business. I just multiply 2 times whatever that acceleration is, and I'm done. So I need to figure out what the acceleration of the system is. And as we've discussed on this call tonight, and I think in other ways as well. One approach is to just treat the 3 and the 2 kilogram block as a single 5 kilogram block with 20 newtons pushing on it. And if that was the case, yeah, we've got a normal force and a weight. They cancel each other out, and I'm left with the net force is the 20 newtons that I'm pushing on it with. That's equal to mass times acceleration, where the mass is 5. So I can see that the acceleration of the entire system of everything is going to be 4 meters per second per second. Well, that's the number that I needed. That's the one that I needed right here. And now that I know what the acceleration is, I can say that the force of 3 on 2 is equal to 8 newtons. Well, I'm not quite done yet because that's either A or B. C, D, and E are eliminated. But this question is asking about the force that the 2 kilogram block pushes on the 3 kilogram block, and that's got to be to the left. Simply because pushing forces are fundamentally electromagnetic forces. These are electrons interacting with each other. They're repelling, so they can only really push away. That's true of all contact forces. So the 2 kilogram block pushes on the 3 kilogram block to the left. And so A is our best answer for question number 2. Lindsay, make sure that I've answered your question. I'm going to wrap up with this call, and I'll have it, once it's done compressing, I'll upload it to YouTube and link it on chapter 2, and probably send an email out as well if you're interested. Okay, that's it for tonight. Have a good night. Don't stay up too late studying, and I will see you all tomorrow for the dynamics test. Good night.